Set theory. Why did it have to be set theory? Hello, and set theory. I don't like set theory, but it's a lesson. So yeah, it's kind of standard to know. They expect you to know it later on, and they don't really teach it fully. They kind of teach it in pre-algebra. They kind of teach it in algebra 2. Kind of teach it in algebra 1. But it's just something I'm just gonna teach. It's kind of like a mini lesson, but it's kind of not. So let's do this. So set theory is the theory of sets, study of sets, etc., etc. So the main thing of set theory is to know the notation. So a lot of things to memorize, but just refer back to this video so I can get some views. I mean you can understand the topic and yeah, so on. But anyways, let's get into it. So you might notice when I've used something like this. So that means the real numbers. What does that mean? And what do I mean when I say complex numbers, imaginary numbers, um, uh, integers, whole numbers, etc., etc. Counting numbers. There are many sets, infinite sets. Actually, more than infinite sets. There's an uncountable infinity of sets. So let's do this. So we can categorize the set of everything in math. So everything in math, every single number, every single, well, not equation, but just every single element. That's what we call it. Every single number, every single, even complex, imaginary, rational, complex and imaginary, everything. It's called a universal set. And we use like a U, kind of like a weird U, but the universal set. I'll explain it when I say it. So the universal set. That's everything. All the numbers. How can we categorize them? Well, we can categorize them as counting numbers, right? 1, 2, 3, ... And we identify a set by putting these curly braces. Okay? So that's a set. Usually we say S1 equals, and that's a set. S2 equals, and then let's say another set, like 2, 4, 6, ... That's another set. Alright, so we can express all these. And notice that when we express S2 as 2, 4, 6, 8, blah, 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 we can also say 2, and then it's the same as S1 minus the odd ones. So on. This one has infinite. This one also has infinite. They both have infinite elements. I'm going to say what an element is in a second, but they both have infinite things in it, numbers in it. Yet it seems that half of this one, half of S1 equals S2. But yeah, but we know infinity is a weird thing. Infinity over 2 is infinity. Infinity plus 1 is infinity. Oh god, so many things like that. So this is the first set I want you to memorize. The counting numbers. Hopefully you memorize it. But before I get to the other ones, I want to talk about what an element is. So there are sets, and they're just groups. Okay, they're just groups of elements. Elements are things / numbers or whatever. Like in this one, the 1 is an element, 2 is an element, right? Yeah. Another set I want you to know is the whole numbers. So the whole numbers is S1, right, 1, 2, 3, 4, but there's also 0. So 0, 1, 2, 3, and I'm sure you don't count. I'm sure when you're counting from to 100, you're not saying 0, 1. You just say 1. Okay, that's just how you start. That's how you've learned it. So there you go. Now I want to talk about another set, and this one is kind of like a combination of the second one and kind of like the first one. It's the integers. The integers. Now this time it goes from negative infinity, -2, -1, 0, 1, 2, dot dot dot. We know about the integers. Next one I want you to know about is the imaginary numbers. So that actually, never mind. Forget what I said. I want you to know about the rational numbers. The rational so notice that these each have infinity, right? Although it looks like this bottom one has more than both more than top ones, and the bottom and the second one has more than the first one, but they all have infinity. That's what we call it, right? Infinity. Now there are two types of infinity. There's countable infinity, which is what this is, right? 1, 2, 3, meaning you can make it into this one, right? This is counting. You're counting to infinity, right? You're counting to infinity. So now any set where you can manipulate it using counting and probability, right? Remember those counting lists? Manipulate it such that you get this. So in this one, if you were to add 1 to everything, you get 1, 2, 3, and that has a countable infinity. You can count. You can. Oh well. So that has infinity. This one has infinity. This one. How can you make that one infinity? Well, it's kind of like adding negative infinity plus 1, maybe? No, you can't do that. Although this one still is countable. All that you're doing is but you can just rearrange this. You can say that's, you can say 0, -1, 1, -2, 2, -3, 3, dot, dot, dot. So you can categorize these. And this is actually just ending up to be 2 times, this is just equal to, theoretically, 2 times infinity plus 1, right? We have the 0 as a 1, right? There's 0 as an extra, and then we have 1, 2, 3, 4, right? And then we have -1, 2, 3, 4. So that's just 2 times infinity. And that's also infinity, right? So this is also a countable infinity. We can count it. Next one I want to talk about now, rational numbers, which is anything in the form a over b. So this time it's the integers, but there's also -3/4, 2/7, all that, and that's an uncountable infinity. And we can't really even count them. We can't say 1/4, 2/4, 3/4. So what we're gonna do is we're gonna just say like this. We're gonna say a over b line a and b are integers, right? That's how we do it, because we can't count it, right? Now where we start is going to be something, if we had 2 elements, right? So let's say we had 1/4 and 2/4, and this is 1/2, but wherever we start and wherever we have 2 elements, we can always find another element that's in between them. In this case, what's between 1/4 and 2/4? Well, the average, right? We'll always find something halfway at least. So we have 3/8. Let's say we added 3/4 here. We can get that to 5/8. What's in between these? Well, 4/8. And notice that's just 1/2, which is 2/4. But we can always find another number, like, and maybe even in between these two, you can find something. These two, and then those two, those two, those two, so on. And that's why it's uncountable, because no matter if you have something, then you can always have another. Now I want to talk about the next set, which is S5, and that's gonna be, hopefully you guessed it. And first of all, you notice a over b. Notice that some things can't be represented as a over b. The square root of 2 pi e square root of 7 negative square root of 7 times e over pi squared. You can't express those as fractions, even though I did use a division symbol. But a and b aren't integers. They have to be integers. Pi isn't an integer. Neither is pi squared. So this is going to be called the irrational numbers. The irrational numbers are all the real numbers minus all the rational numbers. So there's 2, root 7. Again, in this one, there's an uncountable amount, right? Now, at 6 is both of them is the transcendental numbers. These ones are really complicated, so I'm not gonna go into them. Yeah. So the transcendental numbers there are many, but some of them but there's pi, e, probably some more. If you don't know what e is, you don't need to, but you do need to know what pi is. I'll talk about e in a later lesson, but maybe for your math enthusiasts, you might know what e is. Of course, you know what pi is. So now, everything combined in this so far is real numbers. We have everything, and again, uncountable. So is S6 uncountable? Answer is probably not, because I don't know, it's not really necessary, so I'm not gonna say anything. Now the next group of sets, I guess, is gonna be the imaginary. So now we're gonna have S8, and that's gonna be the imaginary numbers, right? I, negative I, 2I. This is a countable infinity, right? I'm just putting examples now rather than in ordered. So now notice that I'm not putting I, 2I, 3I, and then after that I'm going to put 0I, 2I, 3I. Then I'm going to put negative. I'm not organizing it the same way as with real numbers, because with imaginary numbers I'm like, oh, come on, just do the same thing again. Just get to the point. And then there's the complex numbers, which is uncountable again. I'm going to keep it there. And the truth is that everything is expressed in a complex number, right? I mean, sure, there might be some numbers, probably, I don't know, but yeah, this is just a plus. Yep, we're gonna have to do the same thing with the rational numbers. We could have done with S7 and stuff like that, but I just feel like doing it with this one, like I did with the rational numbers. A and B are integers. Okay, and then of course there's S10, which is everything, called the universal set. Okay, so now we know these sets, right? We know what an element is, what a set is. Now I want to talk about studying the sets, because these aren't the only sets. There's so many sets. I said there were infinite sets, right? Uncountable, infinite, right? Because there can be, you can categorize them in any way. You can categorize them as all the numbers that are in the form 3n plus 1, all the numbers that are in the form 4n plus 1, 5n plus 1, 6n plus 1. You can also say all the numbers that are in the form 7n minus 2, 7n squared plus 2n minus 3, right? Anything. So, when we study them, there's some notation we use. So first of all, there's this symbol, and then of course with that comes the symbol with the cross. So what does that mean? That means is in. This means is not in. So if we said 3, that thing, and then we did our set, maybe we did counting numbers. Sorry, what am I doing? So we had 1, 2, 3, ... What this means is that 3 is an element of the set, this counting number. So when I say that 3 is in this, you see right there, there's 3. 3 is right there. Same as 2, same as 1, same as infinity, theoretically. Okay, that just means it is in. But if I had 0, that is not in the counting numbers. It's not in, or sorry, there's no 1, or there's no 0. There's a 1, 2, 3, 1, oh my god, 2, 3, ... You don't see it anywhere. It's nowhere to be seen. So it's not in it. Okay, now I want to talk about, what if I were to say that 2, 3 is in 0, 1, 2, or yeah, sorry, no, not parentheses. 2, 3 is in 2, is it 1, 2, 3, 4, ... That is not the right notation. Although what it is implying is that 2 and 3 are in this. So this set is contained in this set. You see it right there, 2 and 3. You can even have 2 and 4. They don't have to be right next to each other. You can have 2 and 4. And hey, 2 and 4. So you don't have to do 2 is in it and 4 is in it. You can do just 2 and 4 are in it. But this isn't the right notation. This element or whatever symbol is for one element. But when we have multiple, we use this. We use this. It's like a C, but more like a U sideways. And then there's also this, right? There's also this and this. It's just when you flip it, right? When you have, if you had the 1, 2, 3, 4 first, and then you add the 2, 4, then you use this one. But in this case, using this one. So what you're going to do is you're going to put this. So this means subset, meaning that one set is contained in the other set. And then the other, and then you can also use this. If you had 0 and -1, you can say it's not in that. So now, what if you had, so now you can also have a line there, which means strictly in subset. So that's a strict subset. So a strict subset is where, like, it's where they're both are in it, right? But like, I'll get back to you on that one because it gets a little more complicated. I mean, it doesn't get complicated, it just gets annoying. You know what, I'll just say it right now. So, it's like, so like, okay, yeah, I mean, you don't really need the strict subset, but the strict subset basically just says that, like, so when you have a subset, that means that if you had set 1 is in set 2, that means, so this implies that S1, or yeah, so that implies that set 1 is in set 2, right? But like, okay, before I get into that, I'm gonna talk about the cardinality. So the cardinality of a set is how many numbers, how many elements are in the set. So if you had S1 is equal to 1, 2, 3, nothing more, just 1, 2, 3. And then the symbol for cardinality is absolute value or magnitude. So what you do is you'd say that the cardinality of S1 is equal to 3 because there's three elements in that set. Now we can get back to this topic of strict subsets. So when S1 is a subset of S2, that means that the cardinality of S1 is less than or equal to the cardinality of S2. But if we had S1 is strictly subsetted to S2, that means that the cardinality of S1 is less than cardinality of S2. So it can't be equal to. You can't have, so in this case, you can't have 1, 2, 3 is strictly subsetted to 1, 2, 3. That's not allowed. If you remove this 3, it is allowed. Okay? So the cardinality of this when I had 3, it was 3 and this was 3. So you can't do that. And the only way for a subset to be the only way for a set to be a subset of another set, like strictly subsetted, is if they are the only difference between these two is that this one you can have S1 equal to S2. That's the only way the cardinalities can be equal, if they are equal. Okay, that was kind of confusing, not gonna lie. Rewatch that part over and over again, please, if you were confused. Yeah, so now I want to talk about what do I want to talk about? I want to talk about something. Oh yeah, so now I want to talk about how do you express every little thing between 0 and 1. So every fraction in between every decimal, e over 7 maybe, everything in that. And then that must be some issue. How to express every single thing, every fraction between 0 and 1. That's gonna be, so you're gonna have S1. So, yeah, sorry, no. You're gonna use, this notation. So, you use parentheses, and you use brackets. Yeah, you can't use curly brackets, so these are the only ones left. So, then you use the commas. And so, you put 0 and 1, 0 and 1. So, when you have parentheses around 0 and 1, this implies everything between 0 and 1 exclusive. What does exclusive mean? That means that it's everything between it, so 1/4, 2/7, e over 5 billion, everything exclusive except for 0 and 1. So you're excluding 0 and 1. What happened? So it just got erased somehow, probably because of these idiots, but it's fine, no need to worry. So when we had 0, 1 and 0, 1, this means, so when we express 0, everything from 0 to 1, then that means that we were, so this means exclusive. But this, when we have the brackets, so when we have 0 to 1, right, this means, so when we have the parentheses, that means that we are including every single number between 0 and 1, but we're not including 0 and 1. In this case, we're doing everything between 0 and 1 again, right, but inclusive. So that means that you're having 0 and 1 and then everything between it. So that means that this is equal to this plus the extra 2 elements of 0 and 1. Okay. So, but what if you combine them? What if you had 0, so that, and then 1? So that means that you have 0. So that means that you have everything from 0 to 1. Everything between 0 and 1. But you're including 0, but you're not including 1. Yeah. So, and then if you had the other way around, so you had like that, then you're gonna have so you're gonna have 0 through 1, right? And you're also gonna have the 0. Or it's so hold on. So if you had, I'm gonna write this down here. And of course it's not working. Why doesn't this work? Whatever. So, oh my god, so dumb. Anyways, when you have this, that's equal to this plus the extra set of just 0. Then when you have this, that's equal to 0, 1, everything between 0 and 1, plus the extra 1. And then one more extra set that you probably should just know. It's called the null set. Either that, or just it's a set with nothing in it. And that just means nothing. There's nothing in it. Not even 0, not even 1, not even e to the 7th. Nothing in it. Oopsie daisies. Now you know this. I might have to end this soon because this is not working at all. Yeah, and whenever you have an infinity, so like everything from 0 to infinity, and let's say you want to include the 0, you can't include infinity because infinity is not a number, so you have to do this. And if you had negative infinity, you have to do that. -3, let's say. Okay. So now, how I like to remember whether you have to do the curly one, or like whether you have to do parentheses or brackets, is look at the infinity. And when you look at infinity, right, you see this. It's like kind of like the same. Kind of see like, well, not even let me switch pens. You kind of like see this curve, and you see this curve, and they look kind of like the same, but the parentheses bigger. So just remember it like that. Because you can never have brackets with infinity. So, or I mean you could, but not like on that side of infinity. Now let's say you want to express everything between 0 and 1 and 7 and 8. So everything between 0 and 1 and 7 and 8, but you're including 0 and including 7 and 8, but you're not including 1. So that means that you're going to have bracket 0 to 1, and you're going to have 7 to 8 in brackets, right? But I don't want to express them as two things, so I express them as one. How can I do that? Well, now there's 4 more symbols. Yay. Wait, 4. I think it's 4. No, 2. So there's a U, a big U, and a upside down U. This is the union, and this is the intersection. That's the intersection. How I remember it is U for union, and other thing for intersection. And then if you had a Venn diagram from pre-algebra, this is the intersection. Where they intersect, that's what they both have in common. That's the intersection of what's happening. So, if union is where you're combining them, and intersection. So union is where like you're combining both the sets. So that means, union means or, kind of, right? And this means and. So this is like what's common between them, and the union is like what's both of the sets combined. So in this case, if you want both of them, you're gonna use a union. So you express it like this: 0, 1, union 7, 8. If we had let's say we had 0, 1, 1, union. Actually, I'm gonna just use them both as parentheses. Union 1/2, 2. That's gonna be equal to. So what do they both have in common? So this one's 0 through 1, and the second one is 1/2 to 2. So they both have in common the 1/2 to 1. But the thing is that this first one doesn't include the 1, but the second one includes the 1. So we're gonna do 1/2, 1. And because they both don't have 1, but they both have everything below 1 until 1/2, we're gonna use that. Hopefully you guys understood. I know this wasn't working. I don't know why, but yeah. Thanks for watching, and I'll see you guys next time. Goodbye.